Funding for this program was provided by the Annenberg CPV project.
The time has come to look ahead for a preview of what lies beyond the mechanical universe.
I have a wonderful story to tell you a little bit later. Right now, I'd like to whet your appetite for it a little bit. You may remember that a long time ago, I read to you a letter that Albert Einstein wrote in 1912 to his friend Arnold Sommerfeld. It goes like this. I occupy myself exclusively with the problem of gravitation and now believe that I will overcome all difficulties. But this one thing is certain, that in all my life I have never before labored at all as hard, and that I have become imbued with a great respect for mathematics, the subtle parts of which, in my innocence, I had till now regarded as pure luxury. That's really a typical physicist's attitude towards mathematics. Mathematics is a tool to be used for other purposes. The subtleties and details of the mathematics themselves are of little or no interest. But Einstein had found out to his dismay that that wasn't always true. The mathematical basis of Einstein's general theory of relativity was something called the tensor calculus. It had been worked out 10 or 15 years before by two Italian mathematicians, one of whom was named Tullio Levi-Civita. In 1914, Einstein wrote his first paper on the new theory. Another physicist named Max Abraham, who had a rival theory of his own, tried to read Einstein's paper, and he just couldn't understand it. It was too difficult. And so, in order to get some help, he sent it on to Levi-Civita. Levi-Civita read the paper and thereby became interested in the theory of relativity. In 1915, Levi-Civita wrote a letter to Albert Einstein telling him that there was something wrong with his theory. Now you can imagine how Albert Einstein must have felt about that. Here he was struggling to master this very difficult mathematics, finally getting up enough courage to write his first paper using it, and the guy that invented the mathematics writes him a letter and tells him that he got it wrong. The issue involved was a particular tensor. A tensor is a kind of generalized vector, a tensor that represented the electromagnetic field. And the question was how that tensor changed in going from one coordinate system to another. Einstein thought he understood how it would work, and Levi-Civita said, no, you got that wrong. In the end, it turned out that Einstein was right and Levi-Civita was wrong. You see, this was a physics theory. Einstein was a physicist, and his physical intuition told him what the answer had to be. But the mathematical steps in his proof were shaky, and that's the point at which Levi-Civita had attacked him. But the technical details of that controversy are not what we'll be interested in. What we'll be interested in instead are the subtleties and nuances of the relationship that developed between the two men in the course of their correspondence.
To the average person, the fact that Albert Einstein didn't consider himself to be an accomplished mathematician may come as a considerable surprise. After all, he had a remarkable command of mathematics compared to the average physicist of his day, much less the average person of his or any other day. What he really meant was that his grasp of mathematics was no match for the brilliant Italian Tullio Levi-Civita. So Einstein's perception was a relative one. But then Einstein was the master of relativity. Of course, in earlier times, there had been no distinction between mathematicians and physicists. Since ancient times, astronomy and computation, mechanics and geometry could be thought of as parts of the same profession. And yet there had always been certain individuals who, like Einstein, had a special intuition about how the world really works. In the 19th century, a new term was coined to describe those individuals. The term was physicist. But even before it had a name, the science of physics had been advanced by two individuals whose command of mathematics wasn't just weak, it was virtually non-existent. One of them was the Honorable Benjamin Franklin of Philadelphia, Pennsylvania, a colony of England in the rather uncivilized Americas. The other, who was born at about the time that Pennsylvania was no longer anyone's colony, was Michael Faraday. Queen Victoria's England. Without a proper education, Michael Faraday found it difficult even to get his foot in the door. But once established within the royal institution, Michael Faraday found a satisfaction that comes only from the pursuit and discovery of original scientific ideas. And though ill-equipped in mathematics, Faraday would do as much as anyone to propel science beyond the mechanical universe of Isaac Newton. Newton's laws of mechanics, together with his theory of the force of gravity, had convinced the world of science that the world could be understood by rational means. Along this same path, Newton's followers would discover that, like gravity, electricity, and magnetism, are also forces that decrease with the square of the distance. The similarity was amazing. And to both Faraday and the scientific community at large, it posed one of the significant questions in physics. Whether gravitational, electric, or magnetic, how could any force act between bodies when they weren't even touching? Here, Faraday's intuitive power really shone, for at this point he imagined that a 1/r² force must be applied by something that radiated outward, like sunlight. Seeing even further, Faraday conceived of lines of force, starting on positive charges and ending on negative ones. And everywhere they went, which was everywhere in the universe, they carried the power to attract and repel. And Faraday's image of magnetic forces was no less vivid than his perception of electricity. One day, Michael Faraday's visions would become the picture of the electric and magnetic field. But his colleagues, each far more mathematically sophisticated than he, demanded a more rigorous expression of his ideas than pure intuition. Obviously, mathematical steps had to be taken. And they were, in Germany by Gauss, and in France by Ampère. But nobody strode more gracefully through mathematics, nor understood lines of force more clearly than James Clerk Maxwell. His was the most penetrating insight into Faraday's ideas, and with an enormous effort, he transformed them into the electromagnetic field theory. The 4 laws of electric and magnetic fields that remain as valid today as they were the day James Clerk Maxwell wrote them down. The fruits of both Maxwell and Faraday's work bloomed during the industrial age and the electromagnetic era, but only because the seeds had already been sown by someone else in a distant land. He'd first made a name for himself as a printer, then an indelible mark on the affairs of state. But in his prime, Benjamin Franklin made some remarkable accomplishments in the field of science. In Franklin's day, the field of electricity, like the New World itself, was green and undeveloped. In fact, all the world's knowledge about electricity could fit into a Leyden jar. The Leyden jar was the world's first means of storing electricity, and Benjamin Franklin used it to revolutionize physics single-handedly. It was with Leyden jars, not lightning bolts, that Franklin made his most important discoveries. He correctly observed that if one object has a positive charge and the other a negative charge, they will attract each other. But if both objects are positively charged, they repel each other. In fact, Benjamin Franklin invented the very terms positive charge and negative charge. But what exactly is electric charge? And what are the factors that determine how electricity does its work? Playing it safe with electricity means understanding a number of quantities, not just charges, but also volts and amps and fields, to name just a few. But no matter which quantity is on the table, it's always taken something to get electricity started. And since 1800, one way has been the electric battery. Giuseppe Galvani, the world's first neurobiologist, started it all by asking a simple question. How can a frog's leg, without the benefit of a frog, have such a large reaction to such a small electrical impulse? His colleague, Alessandro Volta, found the answer. And by the time he had it all worked out, he'd also invented the electric battery. Of course, the battery's come a long way since Volta made his voltaic pile, with various metals separated by the odd scrap of cloth, clay, or almost anything that was handy and moist. But although the battery could get electricity flowing, it would take something considerably more powerful to turn the wheels of commerce and industry. For example, consider the roundabout progress of the Dutch. In Holland, they made profits anywhere wind rose and water flowed. And throughout the Western world, this energy source was hailed as the wave of the future. But business conditions tend to change. And change they did when the steam engine came along. At precisely the same time in history, coal was being added to the equation of energy sources and industrial power. Coal proved to be more reliable than wind and easier to transport than water. But a different element would soon enter the picture of industrial power. It was electricity, and no one had a better grasp of it than Michael Faraday. He invented a device that twisted because of the magnetic field created by an electric current. This was the world's first electric motor. But Faraday went much further. If an electric current creates magnetism, he wondered, could a magnetic field create electricity? By way of an answer, Faraday discovered electromagnetic induction. By increasing or decreasing the current in one electric circuit, the changing magnetic field he created induced a current to flow in a second circuit. And to one man, that image would suggest unlimited possibilities. His name was Nikola Tesla. Adding an ingenious twist to Faraday's discovery, he came to America to create a vast electrical power grid and to spin like a dynamo into the modern industrial age. In theory, the theory of alternating current, it was smooth sailing for Tesla. But in practice, Tesla met with the most powerful resistance on the American landscape. Thomas Edison seemed to be the force behind just about every bright idea under the sun. The phonograph, the motion picture camera, the ticker tape, and of course, the light bulb. But unlike the glow he'd put in this historic house, the glow in his heart was faint indeed toward Tesla and his idea of alternating current. because Edison felt that it was direct current that would propel America into the future. But the so-called War of the Currents wasn't the only controversy brewing in the late 19th century. The year was 1887. The place, Cleveland, Ohio. And the experiment, the earth-shaking Michelson-Morley experiment, was designed to detect the motion of the Earth through the luminiferous ether, the medium that was supposed to carry light from the sun to the Earth. The methods were conceived by Albert A. Michelson, and no experiment in history had been thought out better and executed with more care. Not since Galileo had so much ridden on a scientific idea. Galileo said that if nothing comes along to interfere with it, an object in motion would remain in motion. That was the law of inertia. And it meant there could be no absolute state of motion and no absolute state of rest. And then Michelson set out to disprove that fact. He was the best and the brightest, the first American physicist to win the Nobel Prize, and he failed. Of course, not finding the absolute motion of the Earth wasn't the only failure in scientific history, but it was absolutely the most brilliant. For one thing, because it meant that all observers, regardless of their own motion, measure the same speed of light. And if the speed of light's the same for all observers, it'd be impossible to figure out one's motion by measuring it. If that were true, when it came to time and space, people could wave goodbye to conventional wisdom. Not that the train schedules would change, nothing so mundane as that. But someone was rewriting the itinerary of physics, and soon, everything that anyone had taken for granted was about to be derailed, past, present, and forevermore. He'd been a relatively poor student, perhaps because the work was too hard or too easy, or because his views were too unconventional from the start. For a quarter of a century, his life remained uneventful, at least on the surface. But in 1905, while working as a patent official in Switzerland, this man saw the universe more dramatically than anyone since Isaac Newton. He was Albert Einstein, and relativity, his way of seeing things, changed the meaning of time and space. If a light switched on as a train passes, it reaches the front and the rear at the same time. Well, that's one man's opinion. But consider an outsider's point of view. In Einstein's relativity, events that are simultaneous to one observer may happen at different times according to someone else. And to see both points of view together requires combining space and time in a single four-dimensional continuum. Looking at the world freshly, and as no one ever had, Albert Einstein saw that according to any observer at rest, a moving clock must actually run slow, and that moving rulers are contracted. And for that matter, he saw much that would change human perceptions about the way of the world. For example, a set of twins, Albert and Henry, born in the same time and space, are on the surface very much alike. And yet on the inside, they may turn out as different as night and day. Being so different and at the same time so alike may be the ultimate paradox of identical twins. In physics, however, the twins' paradox takes off with another image. This is Brother Henry's first time away from Albert. His destination? The planet Zog, 10 light years away. If he could compare his clock to his twin brother's, he'd find Albert's clock running slow. And if Albert could compare his clock to Henry's, he'd find it running slow. And no matter how it looks, that spells paradox. But when it comes right down to it, what does that, and countless other mysteries throughout the mechanical universe, mean? It means a journey into the atom itself, into electricity and magnetism, relativity, thermodynamics, and more, into a realm previously unimagined. It's a realm where even the laws of Isaac Newton have to give way to new and more profound insights, giving birth to a new science, a science that would come to be called quantum mechanics. In all, it's an adventure that's called the mechanical universe and beyond. And beyond all else, from beginning to end, it's the story not only of laws and principles, but of the people who discovered them.
Okay, let's get back now to Einstein and Levi-Civita. That first letter I told you about from Levi-Civita to Albert Einstein doesn't exist anymore. As a matter of fact, in all the correspondence, we have all of the letters written by Einstein and none of the letters written by Levi-Civita, with one exception for a reason you'll understand a little bit later. The reason for this is because Levi-Civita, being a meticulous mathematician, carefully saved every letter he ever received. But Albert Einstein, who had quite a different sort of character, threw everything away. That doesn't matter, though. It's easy to reconstruct the entire correspondence just from the letters that we do have, the ones written by Einstein. Another thing is that the correspondence was very intense. A lot of letters exchanging hands in a very short time. In fact, so quickly that it couldn't possibly happen today because the mail service isn't good enough. But it was possible in 1915. So we don't have the first letter, but we do have the first reply, Einstein writing back to Levi-Civita, who had written to him criticizing his work. Einstein writes, "Highly esteemed colleague, you are giving me great pleasure by paying such meticulous attention to my work. You can imagine how seldom it is that someone with an independent and critical perspective concerns himself in detail with this subject. When I saw that you directed your attack against the most important proof of my theory, purchased with streams of sweat, I was not a little alarmed, especially as I know that you master these mathematical things far better than I do. But, after a thorough consideration, I nevertheless believe that I am able to maintain my proof." The second letter from Einstein to Levi-Civita is dated just 12 days later. In that letter, we start to see the beginning of the relationship that develops between the two men. He writes, "I would be very glad if you would write to me next time in Italian. As a young man, I spent over half a year in Italy, and at that time I also had the pleasure to visit the charming little town of Padua." Levi-Civita was a professor at the University of Padua. And he goes on, "I still enjoy making use of the Italian language. On the other side, I could not muster enough courage to write to you in Italian, as it would turn out to be too clumsy and unclear." Now, undoubtedly, Einstein really wanted to get a letter in Italian, which he must have enjoyed reading, but he's also doing something else. He's busy seducing Levi-Civita. And in the next letter from Einstein, we can see the results of that. He says, "My dear colleague, just now I received your letter of March 23rd, which has been written in the familiar Italian that I have missed for so long a time. You will hardly be able to imagine what a pleasure it is for me to receive such a genuine Italian letter. When reading it, the most beautiful memories of my youth come alive." And then in the next line, we find out that Levi-Civita knew how to play the same game. Because Einstein goes on and says, "You also make it very nice in your letters. First you pat me in a friendly way, so that I, when reading your new objections, do not make an ill-humored face." In the next letter, we find out why there still exists one of the letters written by Levi-Civita to Einstein. Einstein writes, "Highly esteemed colleague, your letter of March 28th, 5 days later, has interested me extraordinarily. For 1.5 days, I had to think continually until I had clearly understood how your example could be brought into harmony with my proof. I enclose your letter again so that I can refer to it without difficulties for you. That's why we still have that letter. And in that letter, there is one of the loveliest postscripts in any scientific correspondence anywhere. Einstein writes, "I have never had a correspondence as interesting as this before. You should see how I look forward to your letters." Unfortunately, all of this has taken place in the spring of the year 1915. In a very short time, Italy and Germany were at war, and there was no way for Einstein and Levi-Civita to exchange letters anymore. The two of them didn't correspond again for 2 years until 1917, when Levi-Civita received a postcard from Switzerland. The postcard said, "Upon my arrival, I found your beautiful new works and took them with me at once in order to study them here at leisure. I admire the elegance of your method of calculation. It must be nice to ride through these fields upon the horse of true mathematics, while the likes of us have to make our way laboriously on foot." All of this, and the two men had never met each other. But what comes clearly through the correspondence is that after the beginning, the controversy itself became unimportant to them. All they wanted it for was an excuse to keep up the correspondence that both of them enjoyed so much. They finally did meet each other personally in 1921, when Einstein was invited to Bologna to give a series of lectures. Of course, that was long after the war had ended. Later on, Einstein moved to the United States, where he lived in Princeton, and in 1936, he invited Levi-Civita to come to Princeton, and the two of them spent a year together. But by that time, the world had begun to go berserk again, and the clouds of war were gathering once more. Levi-Civita returned to Italy, and in 1938, when the racial laws were passed by the Italian fascist government, Levi-Civita, who was Jewish, lost his professorship, lost his membership in all scientific societies, and eventually died isolated from the rest of the scientific world in his apartment in Rome in 1941. Later on, when Albert Einstein was asked what he liked best about Italy, he said, "Spaghetti and Levi-Civita." I'll see you next time.
Funding for this program was provided by the Annenberg CPB project.
You can order these programs on videocassette. Call 1-800-LEARNER and visit us at www.learner.org/channel, the Annenberg CPB channel.